So first of all, I'm the organizer from AI Thinkers Rome. I think one of the most beautiful things about these kind of rooms is that ideas float around, right? They kind of contaminate one another. And this project is very cool because it is exactly this. There's a couple of people in this room right now, which are Nicola and Fabrizio. No, not anyone. But we ended up in a call, reading the paper. And we met through AI Thinkers in the community. And we ended up working on a project, which is what we're going to talk about today. Okay? So we're going to talk about, okay, there's still my screen on top. Wait a sec. Yep, there it is. Okay. So, transformers. If you don't know, what transformers are, is they are the core of LLMs. Right? So they're the very engine that runs beneath it, that makes it work. And we're going to go through something that is very niche, but I think is really cool. And I think it kind of reminds us of the way we think. Right? Not exactly only how LLMs think, but the way we humans think. Okay? But first, let's go through what transformers are and what do I mean by latent space, which is kind of an odd way of phrasing something, right? Well, there's a relatively easy way of conceptualizing transformers. Like, we know that transformers usually have text as input. Okay, let's get that as random. Okay, we usually call it tokens, but let's say it's words. Okay, what a transformer is repeating a series of transformer blocks. Okay, which are these things that you see here. Okay, now they look complicated, but it's not complicated at all. What it is basically you have the words. There's two phases. In one phase, you have the words communicate with one another. So you have a list of the words, and they share information between one another. This is called attention, by the way. And the second component is a part in which the information is stored. So the information is crystallized. So first you have communication, and then you have storage of information. Now this thing actually happens several times in the transformer. Okay? And the idea is, of course, the transformer doesn't think in words. It has words in input, it has words in outputs. The transformer thinks in a numerical way. It uses a vector representation, it's called. And you can think about it a little bit as kind of your intuition, right? You're not always thinking in words in your brain, right? Sometimes the thoughts that you think, they're somewhat abstract. Okay? And this is kind of the transformer, by doing these operations one after the other, he's basically thinking in his head. Right? And then it outputs a token and goes on. So what happens is usually transformers have a fixed number of those blocks. Let's say 3. Okay? So what they do is they take an input, say it's text, and they pass this vector representation to the next one. And the vector is, you can think about it as a point in space, okay? And then you pass it to the next block. And this block, again, does the processing and kind of moves on with the understanding of the concepts. You can kind of visualize it this way, right? If the vectors were two-dimensional, so there was a list of 2 numbers, right? You would have representation from the first block, so it would be a list of numbers here. It kind of represents what the compressed information of the transformer up to that point is. Then you move it to another point with the next block. Okay, very simple. This is what's called the latent space. The latent space is the space in which those points live. In this case, it's 2-dimensional space. Usually it's much larger. Now, we said it's fixed length. Okay? The thing is, many times transformers don't perform very well, because, and we need them to use test time compute. So we train them. Then, sorry, I just realized I'm walking right in front of the slides. They don't perform very well because we train them, they stay fixed, right? And then the performance is stuck. It doesn't change at all because we stop the training. And then we all know R1 and reasoning models, for which this is not true anymore because they reason, right? So they think out loud, and they go through the possibilities, they backtrack, they answer better if they spend more tokens, if they talk more. Now, a few researchers ended up thinking, okay, what if instead of talking more out loud, we talk more in our head, kind of, in the transformer, right? And so the idea is, we have fixed loops here, right? Let's find a way to instead reuse those loops, okay? So it's not a fixed number anymore. Yeah, it's very basic. So as you saw before, you had these 3 blocks, let's say. And now every block, you're using it multiple times. It's kind of a way of compressing the block. Okay, why is this kind of interesting? Well, it kind of changes the paradigm in which you train. So the idea, very basic idea, is when you're training, you don't just have the model do that processing and always in the same way, but you kind of challenge it. So every time you give it a different number of, you sample it randomly, a different number of loops, a different number of operations that it can do. And so the model kind of learns, adapts, and overcomes in the meantime, and learns that it doesn't have a fixed number of loops, so it has to learn to use, if it uses more, it works better. Okay? And the cool thing about this is, if the model learns it, then after you've frozen the model, it's going to learn that the more it uses it, the more you give it, then the better it's going to do. And if you look at the paper, it's basically what the plot tells us. So the more loops you do, the better it does. So why is it interesting for us? Well, that picture that we took before, so this was basically, representations from one block to another. Now this is a single block. This is usually called in dynamical systems, if any of you comes from quantitative backgrounds, is an attractor. So an attractor is kind of a word in complexity theory and dynamical systems. But the idea is, we're not heading straight towards a single point anymore if we're looping those blocks. So if we're giving more opportunity to process data, but we're gravitating around kind of a concept in this space. So we're not going straight into it anymore. We're kind of gravitating around it. And the more we spend time computing, the closer we kind of get to the center. And so that's why the looping kind of works. And so this was what was done by the paper so far. So nothing. What we thought was, and the paper only did it for one block in the middle. All other blocks were the same. Okay? So think you have a regular transformer. All the blocks are just one, not looped, so you only use them once. And then there's one in the middle and you use it many times. What we thought was, okay, but we can kind of generalize this. And what if we think of every single block in a transformer as this attractor, as this concept that the tokens gravitate around instead of jumping right into. And so it's what we've done. And we've trained a model of this, I will show you later. And the idea is, it's kind of messy, but we actually put 2 different looping layers, so 2 different blocks that are randomly acting in sequence. And what happens is, so the model starts at 0. It enters the first recurrence. So the idea is, it finds like some concept to gravitate into. It then stands there a little bit to refine the idea. I think it's very similar to what kind of humans do, right? Because before we're certain about something, we kind of, in our mind, refine a little bit the details, and then we move on to the next component. And then we do it again. And so this is kind of, before, this was just one big dot, right? But now we're refining it very slowly. And so I think this is very interesting to see it as excuse my graphics, as a generalization and a way of seeing it as a multi-skill problem, right? Because before, this was a single element. Now we're both modeling the outer loop, so the outer recurrence and the outer understanding of the model, but also the inner one. Okay, so we're also going into the details and trying to explain computer refining our representations. So before I dive into kind of a little demo, but it's very easy, simple. Why would we need this? Well, first of all, it's not obvious, but if you can reuse layers, kind of an ecology kind of way of thinking about it, you're actually using less compute, at least in storing the data, right? Because you're reusing the same processing instead of having a new one. I talked about a little bit the multi-scale modeling. This is what I meant before, because you're refining the information on one scale, and then you have those attractors that move around. And the idea is, this makes sense if you think of a so-called Platonic representation. Many of you who are familiar with the literature know this. There's a kind of an hypothesis that concepts are ideal concepts, and Plato said this. And there's in the literature something that kind of discusses how there's really a geometry to these concepts in this space. So this kind of says, okay, concepts have details, let's also discuss those details, and let's also discuss the geometry of the details and also the big picture, right? Also, sometimes the thinking tokens are not available. Like I trained the model, one of my latest research papers were about a model that does prediction of molecular structure. There is no deep seek for a molecular structure because that model doesn't have tokens for that reason, that have language. Those tokens are atoms. So if the model uses more carbons, it's not going to help them to answer the question. And also, something that's really interesting that Nikolai very recently focused on, I think it's very interesting, is, okay, do the attractors look different based on what kind of word it is? I think it's really key, right? Because we are focusing more on the details of the representations. We're going a level below. And so maybe we can see that there's some kind of structure that we can actually interpret from that geometry that we're unraveling. Now, I'm done with this part, and I'll show you very quickly this model will work. We're going to see a real time, a small model trained by me last night, which is thinking this way. Okay, so we're going to see the representations are going to loop, and they're going to be closer to one another. So we're going to, that was already on. Okay, let's keep it this way. We'll start a new generation. And the prompt is, hello world is a test, so it's nothing special. We're not expecting special geometry. But what we're going to see on the right is the last 5 tokens, so a zoomed in trajectory, right? So there is where you're going to see the model loop a little bit. And on the left, you're going to see the big picture. So as you can see, there's tiny clusters where the models are going. Okay, this is a new token. So you see they're forming tiny clusters, and this is a zoomed in version of that tiny cluster. And from time to time, it's moving on to the next tiny attractor, and it's jumping around. You see they've done 3 because this is 3 looped blocks. And this is, as you see, the block at some point starts turning inwards because it's gravitating around the concept, and it's trying to refine the representation of that concept. So, thank you very much. And if you have any questions, you can find me later.